Europa is a moon of Jupiter that might have life in its ice-covered ocean, and we're going there in just a few days. By we, I mean NASA, but I got to sit down with a NASA scientist who's on the Europa Clipper mission team to talk about all things Europa. The first half of our discussion is about Europa's geology and the implications its geologic activity has for its habitability, its ability to have life in its ocean. And that part of our discussion is in this video. And then there's a part 2 to our discussion, which is going to be shown on GeoSociety, the Geological Society of America's channel. And that is all about the Clipper mission specifically and what it plans to do when it gets to Europa, all the things it might discover on or potentially in Europa. So be sure to check out that part 2 video after watching this one. But without further ado, let's get into this video about Europa's geology, starting with an introduction to our scientist, Dr. Erin Leonard.
Thank you so much for having me, Rachel. My name is Erin Leonard. I work at JPL as a research scientist, and I'm also a project staff scientist for the Europa Clipper mission.
Awesome. Thank you so much. That's so exciting, but we'll get into
we'll get into all
that. So we are at the Geological Society of America GSA Connects 2024 meeting, and I am working with them to promote a lot of the work being presented here at the meeting. And you have multiple projects that you are presenting here or on, you know, as collaborators, and all about Europa. And so I want to get into kind of the details of your projects. We'll start with the one that's more about Europa's geology. Actually, before I say what it's titled, is it cycloids or cycloids?
Cycloids.
Okay, got it.
Yeah.
The title of this project is Europa's Global Trends in Microchaos and Cycloids with Implications for Geologic History. And so this is, you know, about Europa's geology. And there was recently a map published, which is really exciting. So we'll get into that. But before we do, can you just provide a little bit of background in terms of what is Europa and why do we care?
Yeah, of course. So Europa, in case you're unfamiliar, is one of Jupiter's 4 main moons. And it's actually one of the smallest of Jupiter's 4 main moons, but not by much. It's about the size of our moon here on Earth. And instead of being covered in rock, though, like our moon is, it's covered in ice. So it has this ice shell with a liquid water ocean underneath and then a rocky core in the middle. And there's actually so much liquid water that it has more than twice of all of Earth's water. So there's a lot of water on this, what we call ocean world named Europa. And we're really interested in Europa because we think it has all of the ingredients to potentially support life.
That's amazing. So we care about it because, you know, life, extraterrestrial
maybe,
life. But what's the significance of Europa's geology specifically? Why do we care about that?
Yes, well, so besides just being super cool as a geologist, I would argue that Europa's surface is one of the most complex in our solar system tectonically, and so it's very interesting just from a fundamental perspective, but also thinking more about the habitability and life perspective. A lot of the geology on Europa is telling a story about the communication between the surface and the subsurface ocean. And that communication or that transport of material from the surface to the subsurface could be a really important mechanism to support life in Europa's subsurface ocean.
Amazing. Yeah, I have a couple videos talking more, you know, not as in depth as you know, but on Europa's geology and the importance of that cycling and, you know, that, you know, just geologic activity in general for the cycling of material that might support life. And it's so cool that we're getting more, we're learning more about Europa's geology. It's so exciting. So before we get into all of the specific, you know, structures and features and geologic stuff going on Europa, a lot of people, you know, see this cold, icy, tiny outer solar system body so far away from the sun and might wonder, how does it have enough heat to generate tectonic activity? What's going on with that?
Yeah, that's a great question. So Europa, we think there's quite a bit of internal heat on Europa, and that's really generated from the fact that it has a slightly elliptical orbit around Jupiter. Jupiter is so massive, and so it pulls and tugs on Europa in all sorts of different directions. And that slightly elliptical orbit means that as Jupiter, or as Europa is orbiting Jupiter, it flexes. It almost breathes as it goes around Jupiter. So you can kind of think of it as flexing in and out. And all of that flexing generates heat in the interior because it's friction, rock rubbing against rock, and it generates all this heat in the interior rocky core of Europa. And also some heat also within the ice shell itself. And so it's not like Earth where we have, molten core, liquid, dynamo being produced and all of that. But its heat really comes from Jupiter, which I think is really interesting.
Yeah, I love that. It's so funny because we here on our planet, we have tidal pull from the moon, but it's so minute compared to and you see why it's so important for those outer solar systems moons when you look at the scale of like Jupiter compared to our moon.
Right, exactly. Definitely.
And it's like, no wonder they're stretched like crazy. That's so cool. Okay, so you and your co-authors just recently published a map, a new global geologic map for Europa, which has a huge, description of all the distribution of different materials and structures across the surface of Europa, of which there are many.
Oh yeah.
which is really cool. And so I think a lot of people might think, well, it's just ice, right? What is the diversity of materials on Europa and how are they differentiated?
Yeah, so that's a great question. And yes, earlier this year, we finally published the first USGS global geologic map of Europa. It's been, yes, it's amazing. It's a huge achievement. It's very exciting. But yeah, there is a huge diversity of geologic features on Europa's surface. And like I said before, it's actually, I would consider it the most complex surface, at least, or one of the most complex surfaces in our solar system. And although most of the material, the foundation of it is ice, there are other materials on the surface like salts and maybe even organics or sulfates or other things that are contaminating this ice in very discrete locations and also widespread locations. And so some of the geologic units that we identify, we'll use bands as an example. We have these bands that are long linear features. They stretch across Europa's surface. They give Europa this really sort of yarn ball appearance when you just look at it. They can range from this brownish orangish color to almost white, kind of like the rest, white blue, like the rest of the surface. But especially the bands that have that brownish orangish color, they have that color because of the salts that are located within the band, and they're very heavily confined right into the band. And so it's very similar to a geologic unit on Earth where you have a different mineralogy, or you're identifying units based on different mineralogy. It's very similar to that, just in ice on Europa.
That's so cool. So yeah, that's one of the things I think a lot of people wonder, and I wondered when I first started looking at pictures of these ice moons, is like, they're just ice. Why are there so many colors?
Yes.
But yeah, the salt content and the different compositions, that's so cool. And so these bands, why do we think they're so concentrated with salts?
Right. So again, this comes back to the communication between the surface and the ocean. We think that these bands are exposing material that was from the ocean, maybe a long time ago, maybe not that long ago, depending on what model you kind of subscribe to. But these bands are almost like mid-ocean ridges on Earth. They're spreading, they have a spreading center, and they're bringing up material from underneath that we think is more reflective of ocean material, and that's why it's more salty. And so this salty material is very confined to this band.
That actually brings up one of the other questions I had is like, okay, it's kind of analog to like mid-ocean ridges. So does that mean there's any like ice tectonics, like plate tectonics on Europa, or do we know? Or could that happen?
It's a great question. And, I think we're going to learn a lot with Europa Clipper when we get there and we have more data. There is definitely hints of things like plate tectonics, whether it's full-blown plate tectonics or more like primitive plate tectonics. I think that question is still a big question. But we do see evidence of plate motions. We see evidence of extension. We see evidence of convergence, although not as much convergence as we might expect. And so it's still a little hidden from us. We see transform boundaries, all sorts of fun stuff. So it has all of the makings of full-blown plate tectonics, but not all the pieces are there, right, to fit it quite together yet. It may also be possible that Europa has gone through periods in its past when it had motions that are like full-blown plate tectonics, but that might not be a constant throughout its geologic history.
Yeah, wow. So yeah, in the map, the first geologic map of Europa, you guys talk about two major types of things on Europa's surface, to my understanding: the materials, like the bands and the different compositions across the material, and the structures, like physical structures. So of the structures, which there are like 11, I think,
something like that, yeah.
At least in the abstract alone.
Yeah.
What are some of the common structures, and what kind of processes, tectonic processes, might they represent?
I think one of the ones that's most like stereotypically Europa, you're like, oh yeah, that's Europa, are these double ridges or ridge complexes even. And that consists of a ridge and then a trough and then a ridge. And these are long linear ridges that run for thousands of kilometers. They're only maybe a kilometer or two across, but they can run for thousands of kilometers. And these things just literally cover the surface of Europa. They're all over. So at the scale of the global geologic map, we're really only mapping the largest of those because we're looking at a global scale. But if you look at the higher resolution imagery, if you go down in scale, down to the regional scale, these things literally cover the surface of Europa in all different directions. And the formation of double ridges is still very highly debated in the community. And so it may involve something more like a dike or maybe two dikes that come up and form these double ridges. It could be something more like strike slip that generates heat and that deforms the ice around it to generate these ridges. There could be liquid water involved. There's a hypothesis where there's liquid water in the subsurface right below these double ridges, and the freezing of that liquid water can create the double ridge. So it really ranges all over from tectonics to maybe there's water in the ice shell to everything in between. So we really don't know. And it's one of the questions that I'm looking forward to answering, hopefully with Europa Clipper, because with some of the instrumentation, as we'll talk about later, we might be able to resolve between those hypotheses or even develop new ones for how double ridges form.
So in your title, you also mention, which I love this term, I don't know who came up with it, but microchaos?
Oh yes, microchaos.
Just what?
Yes. So first, I guess I'll step back. Europa has one of its major geologic terrains is called chaos terrain. And it's fun. And it's really chaotic. It's appropriately named. But really what it looks like is you had a bunch of double ridges and bands and stuff on the surface of Europa, and then you broke up that surface and mixed it all up. Kind of like you took a puzzle and you broke up your puzzle with all its puzzle pieces and you mixed it all up together. So there are some plates within the chaos that you can actually reconstruct back together to the sides of the chaos terrain and make it look like the pre-existing surface. And then there's all of these plates and knobs and all of this stuff in the chaos terrain sits in this matrix material. Some of it almost gives the impression of chunky peanut butter. Some of it's so mixed up you can't reconstruct it to where it used to be. So it's very chaotic. And those are large scale terrains, right? And then we have what we call microchaos, which is chaos, but on the smaller scale. And so these are more like 10 to 50 kilometers in diameter. Larger chaos regions can be hemispherical in size, they're very large. But microchaos are 10 to 50 kilometers in diameter. They have very discrete edges, and they don't really contain these plates as much. Again, more of the chunky peanut butter texture instead of the plates that you can really reconstruct very easily. And it's really kind of a catch-all term for all of these smaller chaos terrains that we can tell are chaos terrains, but they're small. They can range in morphology. Some of them are more uplifted, and we call those domes. Some of them are more sunken in. They're more like pits, and everything in between. Some of them are just like colored spots on the surface, and we call those spots. So microchaos kind of encompasses all of those things, pits, domes, and spots. And so we use this sort of catch-all term at the global scale because, again, we're at the global scale. We're zoomed out. We're not doing a very detailed map of the surface on a very local scale. And so we're trying to create a global picture, a global consistent picture of Europa. And so we classify these things all together at the global scale.
That makes sense. So possibly my favorite are the cycloids.
Yes.
Because I read a thing, and this might be wrong, that's why I'm asking, but I read once, I think that the cycloids are features that indicate that the ice shell is rotating independently of the interior of Europa because it's completely separated by the water. Is that a thing?
Potentially. So it's definitely one of the hypotheses for cycloids, but the primary formation mechanism for cycloids, so for those who are unfamiliar, cycloids are these large arcuate ridges that are connected by very sharp V-shaped cusps. So arc, V-shaped cusps, arc, cusp, and they can go on for thousands of kilometers across Europa's surface. And they're very unique to Europa. As far as I know, they haven't been identified anywhere else in the solar system. And we think these form, kind of going back to how Europa is experiencing tidal stress as it orbits Jupiter. that flexing generates a very cyclical pattern of stress on Europa's surface. And if you trace out that pattern in these locations where the cycloids are formed, the cycloids follow that peak extensional stress through the tidal cycle. So it kind of creates these arcs and then cusps and arcs and then cusps. And you can think of those as like an orbit around Jupiter. Yeah.
That is so
super cool. Yeah. It actually fits really well. There are some cycloids that are weird or wonky and they don't fit that model perfectly. And so there has been an alternate explanation that in addition to this tidal stress, maybe you need what we call non-synchronous stress or even true polar wander also. Non-synchronous stress is if you think about Europa's ice shell and it's sort of free floating on the ocean, right? And so it might be turning at a rate that's slightly different than the rocky core in the middle, and that generates a lot of stress, and we call that non-synchronous stress because it's not synchronously tied to the core. However, in the work that I've done and in the global map, we actually don't see a lot of evidence for non-synchronous stress, or I guess I skipped true polar wander. So true polar wander is when the whole ice shell doesn't just rotate at a different rate than the rocky core, but it actually just wanders in all sorts of different directions.
True polar wander. That's amazing.
Wanders in any sort of direction based on maybe a mass anomaly or something that it's trying to make up for. You can kind of think of it as like trying to the ice shell trying to reorient to help adjust for some mass anomaly or mass deficiency in different parts of the ice shell. And this has been proposed to explain some other surface features on Europa that I call arcuate depressions. They're also called crop circles just because they're really weird looking. So Europa has great names for its geology. In the global map, we find that those arcuate depressions are some of the youngest features, and they seem to even post-date the formation of cycloids, predominantly at least. But we don't see any evidence of true polar wander in the cycloids, because you can imagine that if it was following this tidal stress pattern when the ice shell was in a different orientation, you should see cycloids forming in all sorts of different directions, but we don't. And at the global scale, we see them forming exactly how we would expect if the ice shell was oriented like we see it today. And so we don't think that there has been, or what we're suggesting is that there maybe hasn't been true polar wander before the cycloids formed. So yeah, I don't know, I think, again, these are all questions that we're going to hope to resolve a little more. I don't think there's any definitive answer. There are some cycloids that don't quite fit the pattern, and so maybe you can explain them as forming more at the time when the arcuate depressions formed. Or maybe we'll just learn a lot about Europa's geology when we get there and get to study it more.
So exciting. So you mentioned that some of these features might post-date others. So how do we know anything about the ages of these things, or is it just relative ages, or do we have a pretty good idea there?
Yeah, so it's difficult on Europa. Europa's entire surface, the average age is about 100 million years old, give or take a factor of 2, depending on how well you think we've constrained the cratering rate in the outer solar system. Because the way we date things in the outer solar system is through the cratering record. Europa's surface is so young, there aren't that many big craters. So we can't do a lot of absolute age dating like this. So we do relative dating. So these are all relative dating, and that's based on cross-cutting relationships. Is this ridge is on top of this ridge, and therefore it's younger than that ridge. So it can be complicated, but we have a general sense of Europa's geologic history only over the past 100 million years, because that's the only surface that's visible to us.
So pretty young.
Very young.
Regarding,
very young.
solar system age.
Yes.
So with that said, I know, Europa's twin from another system in Saturn's system, Enceladus, also is one of these icy moons with a subsurface ocean, and it's got like these active plumes that are always pushing out material potentially from the subsurface ocean at its south pole. Does Europa have any plumes? Are they constant like Enceladus, or intermittent? How is that?
You're touching on all the great mysteries that we have about Europa. So there have been tantalizing evidence of plumes at Europa that have been seen by the Hubble Space Telescope. But we don't have any like nail in the coffin, oh yes, that's definitely a plume evidence at Europa.
And I remember looking into this and seeing some maybe?
It's not, the plumes aren't always there when we look at Europa with the Hubble Space Telescope. So it could be that they're more sporadic. It could be that they change location a lot. They're not as consistent as like the South Polar plume on Enceladus. There's also, reasons to well, we know that it's going to be harder to detect a plume on Europa, especially from far away using space or ground-based telescopes because of its size. So Europa has 10 times the gravity as Enceladus. It's quite a bit bigger. Enceladus is so small. So it's Enceladus is spewing out material, and it departs quite far from Enceladus, so you can see it really well from a telescope.
I thought about that.
Right, but Europa with 10 times the gravity, even if it was spewing stuff out at the same rate, the plume is going to be a lot smaller. So we might not see it very well from the space telescopes or the ground-based telescopes that we have today. But
that's why we have to go.
That's why we're sending a mission there. So
that's amazing.
And plume search is definitely up there as one of the priorities for Clipper.
Is there anything else you want to mention about the geology of Europa before we move on to Clipper?
Man, I just encourage people to take a look at the surface. It's insane. Like it really blows my mind every time I look at it. I've done high resolution mapping on Europa. I've done this global scale mapping of Europa, and it blows my mind every time. So it's really a unique place, and I'm so excited to get even more images of Europa's surface from Europa Clipper. You know, what we have now is going to just pale in comparison to what we're going to have in just a short time, in about 7 years.
I know. I'm so excited. Has there been a mission previously that's come close and takes some good images? Or
yeah, so primarily the data that we use is from the Galileo mission, which was in the system from 1995 to 2003, and it was performed flybys of all the moons in the Jupiter system, was also studying Jupiter. And so we have some images from the Galileo spacecraft. We have little postage stamps, a couple little places that are down to 6 meters per pixel, and that's our highest resolution that we have. And then at the global scale, we probably average out at about 1 kilometer per pixel or so if you're looking for consistent coverage across Europa's surface. But there are some areas, especially near the poles, that we haven't imaged at all.
And so we're going to get that with
Clipper, and we're going to fill in some of those gaps where Galileo there's only 20 kilometer per pixel data. So there's going to be some really fun discoveries too that we find with the Clipper mission, because we're going to end up getting about 80% of the surface at, I believe it's about 100 meters per pixel, and that's going to be just a data set that is spectacular.
Okay, so if you want to check out more on the Clipper mission, I'm going to continue talking to Erin on the GeoSociety channel, GSA's GeoSociety channel. So go over there to check out part 2, because we're going to have a full focused conversation now about the Clipper mission, its major science goals, and all the amazing things that we might discover from it. So go check that out now.